let's leave them on so that
Okay.
we know that they will work. Don't worry.
Thank you.
Sparkling-ish,
No.
non-sparkling-ish. Okay, the sparkling one is also non-sparkling. I think there were quite a few people at the registration desk. I was wondering if they were
Okay, welcome everybody. It's 9 a.m. We will wait another 5 minutes because there are some people in the registration desk yet. But yeah, we will start in 5 minutes. In the meantime, you can go to the web page and start looking.
Did you update the schedule?
Of course I did.
Of course you did. I was just useless.
It's already live.
Future's now.
We don't have hoodies?
There's one.
I have one, Julia. I also have that.
What?
I also have it.
Yeah, of course you have it. I know. slides that I did at.
Yeah. So it's this
It's the slides that I did at.
LPS. Yeah.
LPS. Yeah.
Okay. Then after the install, we'll go into this one.
Yeah. I would show the benchmark, the raster benchmarks.
I mean, you can Google it here if you want.
Yes. Okay, right. What did I do? Oh, it's not there.
It's in the PR.
Vector ones are already here.
Okay.
For some reason it's not. I don't know why. I think
That's the one.
what?
That's the one.
I think it was a good call to take
5 minutes.
take the 5 minutes because a lot of people the registration. Right.
Should we take another 5?
What?
Should we take another 2 more? Like there's this. Give me 2 more.
We wait till everyone's seated
Yeah.
and then we start.
Yeah.
Right?
So
We've done.
I mean, seated and with the laptops out.
Yeah. Just no rush. No
rush.
no rush. There's. Okay, now we also can do. When we were 10 people, I thought we could do a small introduction round.
No, not anymore.
Not anymore. But with 10 people, I would have said everyone can say
Something. Yeah.
a sentence what they expect and what they want to use it for.
Yeah.
Not anymore.
Yeah. Okay. That's good. Yeah, stay here. Hi again. Good morning, everyone. We will start now. It's a little bit late, but yeah, it's fine. I'm Lázaro Alonso Silva, and my colleague Felix here.
Yeah, I'm Felix Kremer. Welcome, everyone. So we're going to give you, I would say, short introduction into Julia for large-scale geospatial analysis. We will start with a first part on general Julia introduction. And so first, to give a glimpse of who's in the room, who of you has programming experience? And who already did some Julia? Okay, so
Good. Yeah. Yeah. So the goal here is to get you started with Julia. So if you have any questions about like installation and what to type or how to debug things, please raise your hand, and then I will come to your place, and then I will get you to the right place. Yes, so more than showing what we can do with Julia, all the features that are there, the goal is for you to get used to it and get you started. And yeah, let's start. I would say, yeah.
Yes. So the other question, so for the preparation, is it, so does anyone had problems installing Julia, or are you all ready set? Because I think we could help you now while, I could help you now while Lazaro is doing the general Julia introduction. So if you have not installed Julia on your local machine, please raise your hand.
1, 2.
And then I come by in a minute. That's good.
That's good, yeah.
I mean, that's what you're here for, right? You will learn, hopefully learn a bit on how to use it.
Yeah, another question that I have is like, raise your hand if you have Windows system. Linux, Mac. 1, okay. That's good, that's good. I mean, it's just, yeah, just to get a sense of the errors that I would expect. So, yeah. Thank you.
Okay, so I start with the general.
Let's go to the schedule first, I would say.
Go to the schedule first, yes.
Go.
Yeah, so we start with a general introduction to Julia, what's different between Julia and Python and R, also how to, just how to do common things in Julia. Then we will give a short overview of the Julia Geo ecosystem, and then we will talk about data loading, data analysis, and then we will also have some time for hands-on work so that you can also start dabbling in Julia. And I mean, all of these times are very approximate. I think we will do we will do some coffee break in between. So there will, I think, official coffee break is between 10 and 10:30, but we will do whenever we see there's a good break. We can just do a 20-minute or so break that everyone can refresh and get a coffee, get something to drink. I don't know whether there will be something to eat, but yeah, we'll see. Yeah.
Yeah. So the next step is the DevTools. So besides having Julia installed in your system, we will recommend to use Visual Studio Code for coding. And after you install Julia in your system, you will need an extension. So you will go to the extensions button in VS Code and look for Julia, and then click on install on that one. Okay, so we will go to your places if you don't have it yet, and yeah, make it started. So the things that we will not use are, oh, there's a typo there. It's called Pluto notebooks. So those are for interactive, reactive cells. I just want to mention it so that you know that it does exist. And Jupyter notebooks. So we will also not use Jupyter notebooks. Yeah, so just a heads up. And now we go into
The introduction.
Yeah, why Julia?
So I will shortly say why at least I am using Julia, or why we are using Julia. So Julia is a relatively new language, was published in 2012, was initially developed by a small team in MIT. It is, and it got public, or it got stable in 2018. And also the Julia Geo ecosystem is still evolving a lot and still bit shaky at some things. Julia is a just-in-time compiled language, so in contrast to Python or R, it is fast itself, so you don't need this. You don't need wrappers in C, C++, Fortran to get to speed. You can do everything in one language. It is optionally typed, so you can give certain objects a type, but you don't have to necessarily do it all the time. It's rather function-oriented, not object-oriented, and it uses something called multiple dispatch a lot that Lazaro is going to explain later. And so what I find nice about this one language approach is that you can dive much deeper into the functionality if you're interested in what is actually going on. Because in Python, you will always hit some C barrier, and then you have to read stuff in a language you're not that familiar with. And in Julia, everything is in the same language, so you can dive much deeper into it. And there's also nice functionality to actually go to the code that is defined to do the function you're currently calling. And so I think that this gives there's a smaller gap between users and developers in the Julia ecosystem, because you can switch certain internals out if you want to. Yes, so that's my take on that. And to the speed, there's a benchmark set up by Christoph Dieber from the R community, and now basically this compares R packages, Python packages, and Julia packages. And as you can see, Julia is faster by an order of magnitude in most of these tasks, and both in the raster benchmarks, but also in the vector operations. I mean, certain things of these, for example, the right is just calling GDAL, because we are, for the input and output operations for a lot of the geospatial data types, we still use GDAL, because why redo something that is basically solved in C. Yeah. So now Lazaro will give you an introduction to the basics of Julia.
Before that, I think we should take 5 minutes to see who has installed Julia and to get things running, because I want you to follow along. So let's do that. So whoever actually wants to run things live here, please raise your hand, or we come to you and then we ask you directly there, okay? So we will do that now. You go there, I go here.
You go here? Yeah. So who has still problems installing? run it from the Julia script here.
Okay.
Thank you.
You install it? Now let's install again. In the terminal, there is a terminal. You should have a terminal there for prompt, for command line. I don't know how it's called here. Yeah, that one. Yeah, that one. Enter. Now wait. Felix will come. Done? No?
I think so.
Oh yeah, Julia robot. Good. Yes, so the next bit I wanted to do it in the REPL, but I don't know. I am unsure if we all are familiar with that, so I think I should show it. Felix, I think we need to do this part in the REPL, but it needs to be in your computer. Should I install Julia here? Okay, let's do an experiment and see if it works. No.
For the fun of it?
Yeah, for the fun of it. Okay.
No, I think you shouldn't.
Yeah, shouldn't. Let's try.
If you can do that, I'm very skeptical of this computer.
Security.
Yes. Seems.
No, just.
I have no idea. This is Windows. This is magic. Yes. Why not install Julia on that?
Yeah. I mean, we are doing this just for fun, okay? It's just like, if it works, it's like, yeah, the security of this computer is not good at all. Like, yeah.
We are doing this because your Mac is not.
Yeah, the main reason.
To connect to the HDMI, right?
Yeah, the main reason is that that Mac, the one that I use, only shows in that screen, but doesn't show in that one. So otherwise, I will be using my own computer for this. But at least this is showing you how you are supposed to install it in Windows. So for those that are using Windows.
You should have tried that earlier.
Yeah. No, but it's good to do it from scratch. So we have time for this. So it's totally fine. I don't know if you noticed, but I mean, I copy-pasted this this line from the official documentation here. felixkramer.github.io BiDS'25 Julia tutorial.
In the meantime, you can show the GitHub repository where you can find all the notebooks.
I mean, yeah, I'm just clicking. Yeah. So that's the main repo for those that still don't have it, okay? Okay, so apparently I was able to install Julia in this Windows machine. I will close this and start again. So let's see if we have Julia here already. Yeah, we have it. This is crazy. Okay. Yeah. So can we all get something like this, please? And you saw how I did it, right? I just copy pasted the thing from the web page, go into the command line prompt, click yes, and then type Julia, and then you should get the REPL. This is the REPL for Julia. And then I will do something that I was not planning on doing, which is like something that you're not supposed to do on tutorials, live coding, because usually things fail. So I will try to do my best, okay?
Also move that, move the code that you want to copy on this screen.
I don't know how to do that. I don't want to copy, I want to type. I want to see both.
Yeah, you will see both. Come on. You do this, and everyone sees that, and you can see this one.
Ah, okay. Yeah, click.
This one?
And then I want to see the other one. Julia?
You see it there.
Yeah. Can I type there?
Of course you can. It's just a second screen.
Okay.
You need to
I still need to use this,
Or
okay.
You tell me what to type.
No. Can you all see the numbers? No, I don't think so. So I always do 2 plus 2, but I don't know if you can see actually 2 plus 2. Can you? Yeah? Just to see that, yeah, it's a normal calculator and you can do that. So the first thing is like simple math, which is in the tutorial. So I just want to repeat the things that are there. Like you can define variables, x equals 5, y equals 2, and the usual thing, right? X plus y will be 7. So that's simple math. You can also do vector map. So I think I should just copy paste as you say, right? I cannot do both.
How to copy paste in
Yeah.
Windows, I don't know.
Okay. So I think I will leave the microphone even though we're supposed to use it. But I will just start typing. So vector map is like you define x equals and then do an array of numbers 1, 2, 3, 4. So I will go through the basics. I know that most of you should know all these basics, but I just want to go fast. So you define a vector, and as you can see, it says that this is a vector of integers. You can do a second one and say this is 2.5, 2, 1, 3.9.
There's a comma too much.
There's a comma too much. Good catch. And this says that this is a vector of floats because we put like 2.5, right? So it promotes all the other floats. And then you can just do x plus y. And then this is an addition like element wise, okay? Each element with each element. So that's the basics for math. There's not much to say. The other one is functions. So there are several ways to define functions and how to use them. One of my favorites is just to say like the normal one, f of x equals something like 2 times x to the power of 2 plus sine of x. Did I type it right? Yeah, I don't know if you can see it at the bottom there. I will put it at the top again. So that's the function now. And now you can just simply say f of a number, and you evaluate that function for that argument, okay? And remember that we define x, right? 1, 2, 3, 4. Then you can apply this function to all the elements of x. And you use the dot here for the broadcast operation. So that means that you need to apply this function to each element in that vector. And you just apply it. There are other functions that are already built in Julia, such as sine or cosine. So the usual suspects, right? So if I just type sine, you will see that this is a function defined for 14 different methods. We will come to that later. But what I wanted to say is that you can apply these functions that are already there, like broadcast them, like apply element-wise with that dot, sine of x, and then you will get the output for that. Are we at the bottom? Yes. Let's go to the top. So all these things that I'm typing are already in the document that is online. So after these broadcast operations with functions, you can also do matrices. So if you define a matrix M equals, there's another function we call ran, like this for random numbers, of course. And you can say I want a matrix of dimensions 4, 3. You get this vector of floats. And then I want to say, give me another matrix called n equals ones. And it's 3, 5 in this case. And you can do this matrix operation m plus n. And it just works. Okay? So you need to be careful about how the dimensions are arranged so that things will work. Otherwise, you will need to define your own element-wise operation. That means that you will need to say element 1, 1 goes to element 2, 2, for instance. So you need to hard code your own custom matrix operation. But in general, math with matrices also works. Questions so far? What do you mean? Just come here, show it.
This is the matrix multiplication of m and the matrix of ones. In Python, you would expect that this is m times n would be the same as n, right? Because in Python, the multiply is matrix multiply. But to get the broadcast, you can just broadcast m dot
mean this one.
Yes.
This one will fail
Why?
because they don't match the.
That's on 5. Okay, yes. Okay, sorry.
Yeah, because that's what I say. You need to be careful about how you have your dimensions on the different edges. Okay? Next up, I think I will go into variables. So we already saw that we can define the variables as this, right? X equals 2. And then you can say simply y. Okay, look at this. Look at this. So y. So first is x equals 2, and then y equals x. So that means that x and y are 2, right? But now if I say x is equal 3, so what is x comma y now? Same thing as before? 3, 3? Three comma 2, right? Why, Felix?
Good question.
Yeah, I mean, in Julia, you don't override the reference to the definition of the variable. So you take the latest definition that you did, but you don't delete the previous ones. That's basically it. Okay.
But that's not only for scalars. If you would wrap everything in a vector, you still have a pointer there.
Yeah, vectors are different. Yeah, I just wanted to show some simple stuff. Yeah, another thing that I want to show, there is a full list of the different data types that are in the Julia ecosystem. You already saw 2 of them or 3 of them. So you saw that we have float 64, right? We have float 32. So those are the ones so far, but we also have like integers, like int 64, int 32, I think. Yeah. So for a full list, yeah, go to the web page. There is a full list of different types. And yeah, also for those that like to have like things like with a low memory print, you also have uint 8 or 16 if you like something. Some people like to encode things on 16, so we can also do that. Yeah, that's basically the types that you could show and see. You can always query the type of a variable. We have x, yeah, we have this x, but let's say I do x equals 2 comma 2 comma 2. Yeah, doesn't matter much. You can always say type of x. Where is the x here? Here. And it will tell you this is a vector of integers and is an alias for an array of integers 64, 1. So if I do x run 2, 2, I will get a different type. So in this case, it's a matrix, and you will see now that it's of float 64, 2, because it's a matrix, right? So you have the 2 dimensions. Okay, I'm getting thirsty now. I'm skipping some stuff from the online tutorial so that we can move faster, and then if we have time, we will come back later to those. The other thing that you have is like in Python, you have your usual for loops, right? So I just want to make some statement here about how you type them. So for, let's say for I in 1 to 3, I actually don't remember in Python how this is. So in Python, do you do print? And then you say I, right? And do you close the for loop in Python? No, right? You just have like the indentation, right? So, but in Julia, you need to close everything with an end. And then you get it. So I think this will be the main difference here. One of the main differences that you will notice between Python and Julia in regards to the notation of how you type things. Let me show you another one. So in Julia, if you want to do a function, if you want to define a function, you do function, I don't know, test name. No, okay, let's call it something different. Function bits, okay? So this function bits takes as input x, and then I think in Python you will just say x or return x. Return x, right? So in Julia you can say the same, return x, or you can simply say x, and by default it will return the last argument in your function. Okay, if I have x and then y and then z, so the last one, which is z, will be the return value. So in this case, I will just say return x. Also, a lot of us use this notation, return x, to be explicit about the thing that we actually want. And if I click enter here, you will see that it's still not working, right? So it means that I need to put an end to that function. And then I have my function bits. So and then these bit functions will just return the argument, right? So in this case would be 3. Or it can even be something else like a 2. It's really hard to type. Or it can be, so what's the difference between those two? The first one is a number, and the second one is a string, right? So the function that I define at the bottom, function bits, is a generic function. So it will specialize on the different input arguments that you pass in. So, I mean, I could also pass a vector, right? In principle, I should get a vector also, okay? Or a matrix. So any input argument that you pass, Julia will specialize that method, and actually on the first run, it will precompile that function so that it's optimized the second time. So the second time, that function will be totally optimized for that specific input argument. That's a beauty, I would say, in Julia. Okay, notation-wise, never forget to include n in all your definitions. Yeah, Felix has this example, this really nice example for a for loop. I will just put it again here. For letter in hello, yeah, I mean, this is totally improvised. It's print letter n. So this basically will loop through every string, right? And then you will get hello, like Hello, hello. Good. So coming back to functions, can you still see the screen? Please, every time this thing goes to the bottom, let me know so that I can start again at the top. Because I just lost track of things. So coming back to functions, we can say again, let's start again with function, function of f1. Then in this case, I will do two arguments, x and y. And I will say now return x plus y. Okay? So what I'm doing now is the different ways to define a function in Julia. So a lot of programmers in the Julia community use this notation, but some of us are a little bit lazy about it, so that we don't want to be typing function all the time. So if the function is short enough, we usually just do f. I mean, we call it f2 just to have a different name. We just do f of x, comma y equals x plus y. And these two are exactly the same. Okay? You can see the signature. It says generic function with what method. And there is another way which I normally, yes?
Can you broadcast only one or two arguments in each function? If you wanted x to be a vector and the sum with only one.
Let's try it. Okay. But okay, what do you think?
I have no idea.
You have no idea. Okay. Let's say I have x. So you mean the following? You mean x is equals to a vector, for instance?
Yeah.
Would be 2, 3, no, okay. Is the 3? Oh, 3, 4. And then I want to say y is equals, let's put it easy, 0. And then you say, I want to have f2 of x, comma y. But in this case, y should be added to x, right? Element-wise. So the first thing is if I can do this broadcast. In this case, it's 0, so you don't see a difference, right? But let's change this to, let's do 1. It's easier to sum. So we will expect 3, 4, and 5, right?
Without the broadcasting?
I don't see a way to do it without a broadcast.
Without
It's the same because x plus y is defined for vectors
Ah,
and
yeah, okay. So,
scalars.
but internally it's doing it for us, right? No, it doesn't. No. I always do broadcast if I have two different input types, basically. And I need to be careful what I'm broadcasting. How would you do it in Python? Can you do that in Python?
Yeah, I mean, yeah, normally I code the function to know already once it will be a vector, and then I treat it in the function as a vector. I was wondering if this can somehow adapt to the input type, right? For the, that is how it works.
Yeah.
If you do not plus but multiply, you can.
No, that one will work. I mean, multiply will work. What was it? Here, right?
Yes.
So I redefine the function like this. What was it? Like that, right? Yeah, this will work because, I mean, you are just multiplying a number times a vector, right? I mean, but in general, I will advise to be explicit about the thing that you want. Otherwise, you will have bugs here and there. Yes?
I mean, what if you did a plus and gave the integer also as a vector? Maybe that should work. Do you know what I mean?
No.
That works.
Come again?
Type it.
Type it.
So if you, sometimes you have this situation that, where am I? So we have F2. So we have this, right? And now you have x equals rand of 1 of 4. I don't know. And now, and you say, and y is a scalar. And now you want to do f2 of so yeah, you could either do this that I know that won't work.
That will work, yeah.
I was thinking of the other way around. Because sometimes you have broadcast and then you want to broadcast over a certain thing but not the other one. And then you can wrap it in either in a tuple, then so that you can insert scalars into your broadcast so that it behaves like a vector. So that won't work the other way around.
Yeah. I usually never go that way. I'm explicit, to be honest, so it's just that. Okay, last one. I cannot click anything now. I think you broke it.
Of course I did. I always do. No, it works. No?
Yeah, no, it works, yeah.
You show magical dispatch?
You show that, please.
No,
Yeah.
you did that. You did a good job showing that.
No, I mean, we already did, kind of.
Yeah, no.
Okay. I just don't want to do with the Python thing. Okay, you remember that I said at the beginning, like, what was it? Can I click now here? Yeah. So when I defined, I think if I did something like function bits, yeah, I did bits, right? So when I did the bits function, I'd said that you can pass like any argument and it will specialize to that argument, right? So we say that. But you can be like very strict about the input types of that function. And every time you call that function with a different input argument, it will dispatch to that method. So coding functions with different restrictions on the input arguments is what we call multi-dispatch. Okay? So, but the name of the function would be the same for all these. So I can do some examples.
Should I?
Do you want to come and do it? Yeah, come and do it. Yeah.
So I mean this is single dispatch because it will only has one argument, so it only uses the type of that argument to define which method it has. This bits function currently only has one generic one method, so it's a generic function with one method. But now we could say, okay, general bits is just give back what you got, but you can now define bits of x, which is like this abstract string. Now we say, okay, if it's a string, just give back. Wait, where's my? I never type on a foreign keyboard. So let's say we do hello. X. And now if I do
control
Control L so that we can
Control.
L. Now we don't see what I defined. That's not so good. But anyway. So this is the function. Now we see the bits function has two methods, and we can even look at the methods. So we can say, okay, what's the methods of that? And then we see, okay, there's one defined for abstract string, and there's one defined for all other types. And now if I do bits of this would return. What do you think?
Hello, Riga.
Hello, Riga. So, but if we now still, but we still have this one, which is just returning anything. And now we can basically function bits is a bad name, but
Bits.
yeah, I just we use bits, and now we say, and then we can do this on multiple levels. So we can have we have multiple inputs, and say, okay, this is x plus y, and now we have three methods, and now we can say something like this is 5, but now we can also restrict this. So with this double colon, we specify the type. So we can say whenever this is an abstract float, we don't want to add numbers, or we just add 2 to it because we can, and then still, so this would return what? You would see that this is still 5 because it's both integers. But now if we do a float here, this would return 7. And now if you do the dot on the other side, so if you input an integer and the float is the second argument, what is the return of that? Any ideas? 5? Yes. I mean, it's becoming a float because our definition is just x plus y, and x plus y of a float and the integer will always return a float because it's automatically converted. But we didn't define a specific function for integer plus or integer and float. We only defined a special function for float and integer. So we could go back and say we can now do this. And say this is x with the time times y. And now this would be 6, I guess. And so basically, and now if we do, so if we replace this one by a vector, or even by a matrix, what do you expect this to become? N is a bad example. Let me just do, is it ones? It's ones. Ones. There's an S missing, right? What would you expect? So ones gives a matrix that is filled with ones on all positions. Why 4?
No?
No.
No? Which one is it now?
Ah, wait, that will give an error, right?
That will be like that.
Okay, my bad. Sorry. But now we can broadcast.
Yeah.
And now what do you expect this to be? So you see ones of 2, 2 is a float matrix of ones at all positions. Just get there. Any ideas? Yes? Yes, okay, you have a question then. Okay, but so this should give 3 on all positions. Question? Yes. Or is this roughly clear or is it totally confusing? If it's totally confusing, we should get a bit deeper into it. Jonas looks confused a bit.
So once again, the declaration of the function for integer and float.
So there's no specific declaration for integer and float. There's only a generic one. There's a generic one for anything and any abstract float, which is just multiplication. And so the broadcast here is basically this bits dot is make a multiply of the integer 3 times the float 1 at all positions, and that's why we get this. If we typing is hard.
Yeah, it's a foreign keyword, and
I think we can force this to be integers. And now we fall back to the definition of anything and anything. Yes.
Can we kindly ask you to use the microphone?
Yes.
I see that one of you are using it, but I think you guys
It's
we don't hear any sound.
It's very hard to. Do we have a holder for the microphone? Because it's hard to type and hold the microphone.
Okay, I will check this, and we might have a solution with this, but
Yes.
can you hold on until then?
Yes, I try, but it's. I mean,
Can I type with one hand? Just kidding.
I can also. I mean, yes.
yeah.
Okay. Any questions regarding that? Yes.
Yes, Pythons. When do you write abstract string or abstract float? And because we could use the normal float.
So this is to use like basically we use abstract. So normally you use abstract types for your dispatch. So the abstract type is never materialized. So there's no, you won't find an abstract float. You can't construct an abstract float. But the abstract float is super type of all the floats. So the idea is that if you take this example and basically force it to use float 32, this will still
Work.
give the same answer as the one before, right? The only difference that you see here between this function call and this function call is that you get out a float 6. Here you get a float 64, and here you get a float 32. If we would have defined, I mean, we can define. If you now say, okay, who needs abstract types? We do it like this.
One hand. Yeah.
We will have a solution for this during the break. So we will find you a mic that you can put on so that you don't have to hold it. The break is in like 20 minutes.
Great.
So
That sounds good.
Yeah.
Thank you. Yes, so if we define this to be x times y, and then we just, no, Oh, yeah. We just add another 2 because we can. Now if we do this, is it this one? No? Yes, it's this one. What do you expect this to be? Because now the ones of 2, 2 is a matrix of float 64. So now we dispatched on the more specific type that it's a float 64. And so we hit this function which adds another 2 to it and not the abstract one. So we normally, so you use this abstract float, abstract string, abstract types to, yeah, so you don't have to define it for all possible floats that you could think of. And the other nice thing is that someone could come along and define a new float type or a new string type. And so your function would still work on these types because you would basically know what is the interface for string. I mean, string is, yeah, I mean, there's some people that define new strings, but we will see this later for abstract arrays. So everything we do is, a lot of the raster data we do is basically is arrays, and so we define a new array type that then can work, that we can then put into any function that would expect an abstract array. If we would use the normal array type for that, that wouldn't work. So you can make it more generic by using these abstract types.
Okay, I think let's leave it at that with multi-dispatch.
Yes.
And multi-dispatch at the beginning is quite like confusing, especially because you use the same name for everything. So sometimes when you have too many methods, yeah, you need to think about which one you actually want to use, and yeah, be careful about it. But yeah, at the end of the day, it's quite useful. So just give it a try.
It's not an uncommon if you know Java or C++, so it's just overloading the function.
But it's more powerful than, it's
overloading. It's different.
overloading is a bit different.
The concept of defining the same function in multiple ways.
Yes. I mean, in Python you would have basically you have single dispatch, because you can define what plus is if you define this underscore underscore plus underscore underscore thing for your type, I think. And so in Python you can define it for you can have single dispatch, but I think multiple dispatch is much more powerful because you can basically define what you expect and what to do with certain types, and then someone else can define a type that follows these specifications, and then it just works together without you having to know about. So people that write the function don't have to know about every possible type that is out there, and people that define a type don't have to know all the functions that are going to be, that the type is going to be used in. There's a more, I mean, I think we could spend at least an hour or so on multiple dispatch, but maybe not today.
Yes. Yeah, I want to move on before the coffee break into some basics of the package manager in Julia. Yeah. Yeah. Ah, yeah.
We didn't? Oh, wait.
We didn't. Yeah.
Okay, wait. Then
Do that one there. Yeah.
is it? Where is it?
Do it there.
No, wait. We had this bits function, right?
Ah, yeah, we did it in Hello Riga.
No, I didn't. I did string
Interpolation.
There I did string interpolation.
Yeah, okay,
Sorry
yeah.
for that.
Just type a new one.
Yeah, just type a new one. Okay, we have a string here. So you could also do this. Hello, where is it? Here. So in Julia, hold it for me, please. Thank you. String interpolation is
It's a product.
a product and not plus. So it's just this. So this will do this.
Do a space before Riga, so we have a space.
So do a space before Riga. Yes. So you can either do the multiplication, or as we did in the earlier function, in the earlier definition of bits, the bits function. I don't know where I did it. Somewhere here. Here in the abstract string case, you have this string interpolation. So with this $, you try to convert every object into a, you try to convert it into a string that to then put into that string. Yeah, that's string concatenation.
Good.
Yeah, and you continue with the
Package manager.
package manager, right?
Yeah, just before the break, because yeah, we are almost there. Can I share also this one in the second screen? No, I don't think so. Okay, I will just do it here then. So now we are in the REPL, right? And Julia has his own package manager. So that means that, yeah, we have a package that manages packages. And you can access this in two ways, I will say. So the first one is by typing right square bracket. So if you type that, I mean, here what I did type this one, okay? So if you type that symbol, like right square bracket, you will go into the package mode. You can see it there, like in blue, right? PKG. So I will go back again, and then that's the package mode. So in the package mode, you can do different things, such as the one that I usually do first every time is to ask for the status of my current environment. So I usually just do ST for short, but you can also do like the full thing, status. Okay. And this is the first time I do it, but it's fine. It's an empty project in this case because, as you remember, I installed here Julia from scratch, so there is not a single package installed here, so it's totally empty. Remember that I also saw that you can say just ST and then you will get the same thing, status empty. The other one is how to add a package. So if you want to add a package, you can do add, and then I will just, for the fun of it, I will just add a random package. Random. Okay? And if I do random, and then you can see that everything is in green, so that means that it was successful. The package random was added. And if you want to check that it's actually there, you do ST status, and then you will see now that that package is now there, random, okay? Another thing that you might be familiar with is environments, right? So the ones that use Python, you have your conda environments all over the place. So what we usually do is create also our own environments for very specific projects. So, and we do that by saying the following. You see now that you are in the package mode here, right? I don't know where I am here now. how do you say in which directory I am in Windows? Dir or dir? I don't remember. No, it's not dir. What is it?
I think isn't it still just try the just try the Unix commands.
I mean, I'm in LU. Okay, doesn't matter. I mean, for the things that I want to.
Just try ls in the shell mode.
For the thing that I want to show is like we usually do activate. So activate is for activating your environment for a specific project. So if you don't want to contaminate your current project with global packages, you would say activate, and then a dot is for the current directory. You can always pass a path here, but I mean, I don't recommend doing that. Just go to your directory and do activate dot so that you are in the right place from the beginning.
Or do activate -10.
Don't complicate things. So I do activate, and in this case you see that the package now changed to the LU directory, right? So before we were in the global one. You see environments project.tom at the top, like .julia environment /v111 blah blah blah. But now our project lives in LU. So all the packages that you install there will be consistent there. And we can see that this directory now, if I type status, is totally empty. Yeah, you see that? I mean, I added random above, but now that I activated this environment here, it's totally empty. There is nothing there. Let me clean this. So I'm just showing the normal commands that you have in your package manager. And now I can say, let's add another package. And now I don't want to add random. I will add linear algebra. Linear algebra. It's fine? Yeah. And that's it. We do a status, and we do have linear algebra now. Okay? But sometimes you are like, oh, I don't need this package anymore. How do I remove it? You just say remove rm, and then again linear algebra. So I don't want linear algebra anymore, and then I just remove it. I do a status again, and now it's empty again, my project. Okay? Another one that is very useful is when a colleague or another team is developing a project or a package, and they share that with you. So they share the project. So when they share their project, they will provide you with a file called project.tom. So that file is automatically created every time you do this. If you do that at random, I cannot show it now, but believe me that a file is created with that specific package, with that specific version. And then when someone shares that project, they will share that also with you. And then if you want to reproduce their results, you want to install exactly the same packages, right? And in order to do that, so you will go into that directory, you will activate that folder, that environment, and then you will say instantiate. And that instantiate will install all the packages that were shared with you. Okay? In this case, there's nothing there, but Felix wants to say something else here.
No, I just wanted to show it.
The project Tom? Yeah, it's Windows. So it's
Windows. I can't. Okay, I don't speak Windows. So.
I don't speak Windows either, so. Yeah, but that's basically it. So remember, you have. Okay, can I share this? Can we share this?
Wait,
one?
I wanted to add one thing for the REPL.
Yeah, go.
Is so if you can't remember any of the commands, there's one very important one, which is the question mark. which gives you a list of all the things that you could do in the package mode. So you can read up on the different things that Lazaro just talked about, and also you can then see what would be possible. And also in the normal Julia mode, you can go to the so-called help mode by just typing a question mark, and then you can get the doc string of every function, or even basically the specific method that you would hit if you do it. So if you do, I think, rand of, I think there should be a special function for matrix. So if you do this, I think it should give you, yeah. So here you saw that this is the first the general sign, and then the matrix sign function. And if you do the this will just, this only gives you the help function of the, or the doc string of the function, or the method of the function that you would actually call if you call it with this argument, or with any combination of arguments. And also a lot of you can always try to tab complete, because tab completion is very powerful. And do you want to say something else on the REPL? Because otherwise I would also say, I mean, you saw it before. There's a lot of REPL history which you can basically go through by taking the arrows, and then if you go back to here, you will basically go back in history. So if you now take the down arrow, you get the prompt that you had after the prompt you got back in history. So it's sometimes very helpful if you want to restart a certain thing. You can go back to the first using or the first activate, and then go down from there.
Yeah. Can we share this one again, please?
Yes, we can. So wait, where is it? Oh.
So one important thing when you use help is that it's very powerful, because sometimes, okay, a lot of people put there how to use the function, and you also see some examples on how to use it. So yeah, looking for documentation about a specific function is easier via the REPL using help than Googling it or going somewhere else. So just to recap, I want to draw your attention to the web page, so you can also see this. This is live. So just remember, the essentials will be like how to add a package, how to remove a package, update. I didn't mention this one, but from time to time you want to update your packages, so you just do up or update. Resolve also is quite useful when you have a mismatch between different versions. So if you don't want to think about how to resolve it by yourself, I usually just do resolve and things get resolved. Instantiate when someone else shares their project. Status, just to see what is the current status in your project. And activate for your current environment. And as Felix mentioned, yeah, get help if you need it. Yeah, all these things that I discussed are described here. And if you want to read more about it, there are some links here on how to get better at it. Yes?
So let's assume I have a fresh installation of Julia. Someone gives me the project, 1.5. So I put it into a folder. So the steps are, I put it into a new folder.
Yes.
I activate.
That folder?
And then I install it.
Yes.
Okay. Without one of these two steps, something strange will happen. Like installing the main, the general.
No. I mean, of course, you need to have a a Julia installation on your computer, but
So if I instantiate without activating,
that will not work. No, you need to activate the environment to see the packages that are available there.
Yeah, because if you don't activate it, the Julia will not use the project terminal that is laying around, but is using you will always have a global one,
Yep.
which is installed in your .julia. So and then one thing to do is like what I think a lot of people have is like you have more general development tools there, which are installed in your global environment. I think I can later show my own global environment. And so you have general tooling in your global environment, and then you have project-specific local environments. And so if you copy a project terminal and lay it there without activate, it won't know that it's there. So the Julia wouldn't know that there's a project terminal around. So it will just use your global one. And then if you activate it, you can. I think it will soon enough start complaining that it didn't have the packages, and then it tells you, and then the REPL tells you, please instantiate this function. There is. I was expecting to have this in this package. I didn't find it. Please instantiate to install all the packages that you want.
Yeah, you will get useful errors.
what is the manifest file which was mentioned there? Next to the project terminal, there was
A manifest, yes.
So the project terminal is basically a list of packages that you want, and in the manifest, so it's just like, okay, I want rasters, and I want here he has like random and thing, and the manifest terminal is you can also share manifest terminals. They are much stricter, so they would specify exact versions. So they're useful for reproducibility. So if you share manifest terminal, you should expect that it works exactly the same, because it would fix the version of all the packages and all the sub-dependencies that you have. And so the project terminal is something that basically you mostly interacted with the project terminal, because you basically via the package manager would add packages, which then would be listed in the project terminal. But then in the manifest terminal, the package manager itself will write the manifest terminal to specify all the dependencies and the specific versions that were used at a certain time. And then sometimes if you add a package, if you already have some packages and then you add a new one, sometimes you change the versions because only certain versions work together, and this will be reflected in your manifest terminal. And so that's why you always get this changes to project terminal and then changes to the manifest terminal.
Would it be enough to just share the manifest?
Yes. You can. Yes, it depends a bit on the goal of what you want to achieve. So.
Yeah.
So.
Just wanted to work straight away.
Yeah.
Yeah, but for that, sometimes the machine also needs to match. So I usually don't share the manifest, so I usually just share the project term. But if I want to be very, very, very specific, like I'm running this in a cluster which is running this kind of machines, then I will share the manifest so that you can actually reproduce the same thing.
Also for workflows that you want to have reproduced, if you say you've done your analysis for a paper and then you want to say these are the exact versions I used for producing these results, you should use the manifest terminal, because there you have actually all the versioning there. And sometimes it's easier to share the project terminal because the manifest terminal also, for example, also specifies the Julia version.
Yep.
And the project terminal is like
Doesn't.
is much freer. It's like it you can specify a minimal Julia version. So you can say, okay, we need at least Julia 1.9, but then it still works if you have newer versions. But with a manifest terminal, it's like, no, we need that version.
Okay, Felix, I think we should break for coffee break. It's 10:30, right?
Yes, I think it's a
So-
good break, right? We are done with the general introduction, and we will have a 20-minute.
I don't know how long is the coffee break.
I think it's supposed to be half an hour, so we can
Let's
also
do
have
half an hour. I mean, the break. I mean, the break is half an hour.
Yeah,
Yeah, but
so
let's
we
do-
do half an hour.
Yeah.
And then we go into the geospatial stuff
Yeah.
after the break.
And yeah, if in the meantime you want to do some installations or something, you have other questions, please don't hesitate to reach out and we can talk about it, okay? Turn off your microphone. The battery is dying. Microphone.
Your microphone. Actually, your microphone is dying.
Just keep the. Okay. Give me. So funny that we installed Julia.
Is the trees?
And if you have complex, just resolve there.
Is the trees? Is the trees?
Funziona tutto?
Test it. Try to speak.
Yes? Is it working?
Yeah.
Ecco.
Okay. Good. So, and this is supposed to be here like this?
We can.
Or is it, should it be more like, I don't know. I mean,
Yeah.
you can give me that and then you can.
Oh, sorry.
That's okay.
Sorry, I know that with the beard.
No, no, it's fine.
I have to do it myself sometimes as well. Okay? Is
Okay.
it better?
I think, yeah, it's okay. If the sound quality is okay, then.
Yeah, there will be a bit of a
I'm
noise,
fine.
but because of the beard, there is nothing we can do about it.
Shave. But not now.
Not now.
So it's my fault. Good. Thank you. So you told me to do what?
5 minutes. It was 5 minutes.
Yeah, but
Dark mode. No, wait.
but where?
You go to
Is it in settings?
settings, theme. No, theme.
Where? What? File? No, view, most likely, right? Appearance.
Appearance, yes. And then
Send mode, centered, blah blah blah. I don't know. Maybe we can do this, but that didn't help. Okay. View. No. File. Preferences. Settings. Dark mode. Dark color theme.
yeah, that one.
No, but this. That didn't help.
Give me a minute. I'm fixing the quarter.
What?
I'm fixing the quarter notebook.
What do you mean you're fixing the quarter notebook?
Didn't render.
Ah, yeah, you do this.
Yeah, but still I went.
But wait, what? Color theme.
Light. Look for light.
Light modern. Ooh! That feels wrong, but I see why you want to do this. Still feels off. It really feels off. Oh wait, I know why. There's stuff, I think you can just delete all of this.
No, let it be. I already fixed it.
Good!
I mean, I didn't delete it. It's just coming out.
So unfair.
We are almost complete.
Oh, I didn't fix the...
Path?
Why is it? Should I try to go into the...
Just go through the notebook.
What? I just go through the notebook, right?
Yeah. Those people will not be running things.
Are we still missing people, or should we just start? I think. What?
I will close the door.
Close the door. Okay. Should I give should I give an introduction to dimensional data or general? Is it somewhere?
Go here to geocosystem.
Oh, mouse.
So we didn't talk about this, so you need to talk about those. Okay? Okay?
Yeah, I can do that.
Okay, so welcome back. So now we're going to talk about more geospatial stuff in Julia. So we first had an introduction to Julia in general, and now we go deeper into geospatial analysis. So first I wanted to introduce the Julia Geo ecosystem, which is basically a GitHub organization and also a group of people that work on Julia for geospatial analysis. So there's basically two types. So there's a more raster focused and more data cube focused set, and there's also some things on vector data cubes. So the main packages that we are using and that I think today I will go mostly in the YAX arrays ecosystem and show how we use that for large geospatial analysis on data cubes, but there's also packages that play along, I would say. So the important packages are dimensional data, which is a bit like X-array using labels for dimension names and labeled dimensions to describe your your data. Then there's rasters, which is basically a sub package of or a dependency on dimensional data for geospatial data or geospatial raster data, as the name says, using all the indexing function in dimensional data, but adding a bit of geospatial analysis tools and also a bit of CRS handling and the specialties of geospatial indexing. And then there's also YAX arrays, which is like a bit like it started out as similar to dimensional data in scope, and now we merge these together. So YAX arrays also depends on dimensional data for the indexing and provides more data analysis tools for large-scale data. And then there's also ZAR.jl, which is a ZAR reader. I think what is missing in this list is ArchGDAL for general GDAL data access, or also GDAL analysis access. There's a geo interface which is mostly for vector data, so it defines an interface for geospatial vector data, like polygons and lines and points. And then there's also geometry ops on top of that, providing operations on these objects. And then for the plotting, we have Maki. We are going to use the Maki ecosystem, which is a general plotting library in Julia, and then there's also GeoMaki on top of that, which would plot data on any projection. But I think I'm not going to go into detail here. And there's Tyler, which plots base maps like OpenStreetMap or any XYZ server. And I just wanted to set the expectations a bit. So I think the certain parts of the Julia Geo ecosystem are very powerful and as powerful. And I think at some points, I showed the speed comparisons, sometimes even more powerful than the Python or R equivalents, but it's a lot less users, it's a lot less polished, so expect rough edges if you find any. So if there's anything that is confusing to you or there's missing functionality, please open issues on the respective packages on GitHub. And if you don't know on which package you should open it, just pick one of your dependencies and open it there, and then we can also sort it out then. But if we don't know about your problems and hurdles you face while using it, we can't fix it. Because sometimes we notice the hurdles, or sometimes we don't notice the hurdles because we are too deep into the stack so that we don't see them anymore. Yes. But with that, I'm going to give a general introduction to Yax arrays and XMap. So as I said, and so this Quarter notebook is on the GitHub repository. So if you want to play along, I hope you could. I'm not entirely sure whether all the fixes are in. And I think I don't need, yeah, I have this, yeah, I just keep it open. So first as Lazaro said, we activate the environment and we instantiate it. I made this pkg.offline so that it doesn't necessarily update certain packages while trying to instantiate. Then this is just, so we load the Maki ecosystem. This is a hot fix for a small bug that I found yesterday that is not in yet, but and then we load all the necessary packages, which in our case is now dimensional data, as I said, for the indexing, Yax arrays for the data analysis functions, ZAR and netcdf are packages to load data, and then glmaki is a plotting library that we are going to use. And so first we load the data. So here we load the data from a S3 bucket, which is in our home institution. So here we define the path to the bucket, the store, and then we define an S3 path. So this is just where the data is located. So this is all using S3 to access it, and then we can just open the data set so this is the set open is from ZAR. So we say normally you won't need this set open, so actually it should work on open data set of a path, but because we want to specify this consolidated and this fill as missing, we need to set open it here. And then so we can run this, and then there's this cube function, which basically, so if we split, can I split that? Anyway, so if we do this here, is it opening? No. Now, and then we convert the data set to cube. So here it's just, so there's a slight difference. So just a quick question: who of you is not familiar with the concept of a data cube, or can I just expect this to be widely known? So so here the difference between this DS, which is a data set, and the data cube is that here we have, so in a data set you could have different data cubes with different dimensions, and a dimension missing or a dimension, and in a data cube you would expect everything to be on the same grid. And so with this cube function you convert your data set into one cube by taking all the data cubes that are on the same grid to then merge them together into one. And then, so here we go from a list of variables that have all longitude, latitude, and a time axis to a data cube that has a longitude, latitude, time, and the variables axis. So just for convenience, I'd say. And here you also see, you already see the size of the data cube. So it's a actually very small example cube. So it's just 144 by 72 in space and 900 something time points and 40 variables. And just for the example here. And now we want to do the now we want to apply certain functions on this. So we have this nice data here, and now we want to apply statistics, for example. And so we can define, so this is the whole idea of Yax arrays is you have this xmap function that's basically you can map along certain function or certain dimensions. So you can say, okay, I start with a longitude, latitude, time cube, and I want to apply one function. I want to apply a statistics function along the whole time, every time axis of every pixel. And to do this, so here we first load the statistics package so that we have the median available, and then we say, okay, and then we define this function, and here we define it like, we define this x with x out and x in, so that you basically always write into a predefined result array. And so this is always the inner function that you would have to write, is like, it gets an output, the output where it should write to, it gets the input that is put into it, and then you can do, here you can do whatever you want, basically. And here we just say, okay, I get rid of all the missing values, I get rid of all the none values, and then I apply the median. If I get rid of every value, okay, then I guess my data there is missing. I don't know what is the median value there. So we defined this function, and now we can apply this function on a whole data cube, and that is where this xmap function comes in play. So xmap always expects a function that we define like this. You could also take, I can go into that later. So you define this function, and then you define what is the input. And here the input is, I want to do it on every, I should have done a, so here I want to do it on every variable which contains the temp string, so on all the temperature values I have. And then there's this so-called O/, which is an operator to say apply on the time axis. So if we do this, because this median function goes from an input to scalar value, so this median of x is reducing your whole time series into one value, you remove or you reduce the time axis. So we saw earlier, so in our input cube had 989 time values, right? And now our output cube has only one. So we did this reduction in time. And now Lazaro wants to add something, I guess.
Yeah. So a lot of you might be familiar with Dask and Xarray in Python to do this kind of operations. And I wanted to say that the main difference here with Xmap is that Xmap will never run out of memory. So Felix here is just showing a really small file, but you can apply this XMAP function to terabytes of data, and it depends on the machine where you are running. It will specialize to do the best that it can be done there. So, yeah, I just wanted to mention that XMAP can run in a cluster with multiple processes, multiple threads, and you will never run out of memory, even if your data set is terabytes. Yeah.
Yes. And also, if your chunking is relatively fine-grained, so it will always try to optimize the access patterns to map the sizes of your data chunks and the power of your machine to add to that. But yeah. I mean, for the example, I mean, we picked a very, very small cube just for the tutorial, because otherwise we would be mostly waiting for stuff to finish. Yes, so, and here we could, for example, just for the fun of it, say, okay, we don't do the median on time, but we do the median on latitude. And now this, as we see here, is all the time points, but every reduction on the latitude. Was there a question? No. Yeah. So let me remove this again. Otherwise I will be very confused. And yeah, I think I should run it again, because otherwise. And then we can just plot it. So here we say, okay, I want to have the value. I want to really have the air temperature at 2 meters. And so now we can just plot it. That takes a bit, because this is the first plotting function we have. So as I said earlier, Julia is a just-in-time compiled language, so it will always have to compile the code the first time you want to run it. So this is in the Julia world known as the time to first plot problem. So we have to wait now for the first time, but then every other times we plot, it will be instant. It's just yeah. Could have preloaded, but yeah. And now we see, okay, this is just a very coarse median air temperature over the whole world, over, I think, 30 years or so. And yes, so now we can also, as Lazo showed earlier, we have this broadcast machinery, so this would also work on these arrays. So you can just apply plus on every value. So you can just do this dot plus here to convert. Now we saw that our results were in Celsius. Now we can just do it in Kelvin and say, okay, I want to add 273 degrees, and then we see that the grid is the same. And then if we plot it, it should be a bit faster, hopefully. So the only thing that changed is basically the color bar, because we didn't change the values, but we changed we didn't change the ranges of the values. So yeah. And then so this XMAP is a very powerful construct. So you can do operations on any input to any output. So you can say, so you can have either multiple input cubes, or you can, in this example, have multiple output cubes. So here the example is, okay, we want to normalize our time series by subtracting the mean and dividing by the standard deviation. But we also want to keep the mean and the standard deviation, because we might want to use it later. So you can just define this function, which has here has multiple outputs. So you have the time axis out, you have the mean out, you have the standard out, and you have the original time series that goes in. And then you define what you want. So first we again filter the missings and nones. And then if it's empty, we define everything as missing. If not, we have this empty brackets, which is basically an empty get index. So basically it says this value is that value. This is because this mean out is a container. So it's like a vector. And now you say, okay, it's a 0-dimensional vector, which, because it only has one, you only want to have one, but we predefined it so that we can reuse it for every chunk. So for this example, it won't matter that much, but if you want to do very large operations, so this is, Yaxo is taking care of that in the background, is pre-allocating the outputs so that it can reuse the output for every chunk that it's iterating through. And so we define this as the mean, we define this as the standard deviation, and then we define this, we do this normalization. And if we now want to apply this, we can again use the xmap function on the norm. So the first input is always the function you want to apply, and the input is CO/ on the time axis, and the output is a tuple. So it's basically this basically means there's 3 outputs. The first one is basically gives a time axis, or has a time axis. So here, because the input is the time and the output is the time, so the size keeps the same. And here, this means the X output is empty, so this means this is a reduction in whatever input you have. So this means, okay, this is a reduction in the time axis. And if we now run this, we can see, if we now look at the grids again, we have this TS norm. So we have this. This is the same size as the input. We have the STD. This is just one element in time, and here it keeps the information that this was basically, it took all the information from all of these time steps between 1979 and 2021, and the mean cube is the same grid as the standard deviation. And now if you want to, and now we can plot it again. Okay, we can't plot it. Why? What did I do wrong? What? It's not downloading the data. Ooh, you mean this is because it's not the local one? Might be. Small glitch. So here we see the, what did I plot? The standard deviation of air temperature over the whole 50 years of 40-something years of data. So we see, okay, in the tropics there's not much deviation, but in the boreals there's more differences between, I think, basically more seasonality. And are there questions so far? Yes. For what? This is currently Quad. So I have this Quarto document for the. I'm not even sure whether it's a Quarto plugin. Is it? Okay. Good.
And it takes half an hour to install everything.
Oh no.
I'm still installing. It's closed now.
Sorry.
Yeah, we did Quarto. Yeah, we prepared the material in Quarto notebooks so that they could be running on GitHub and just deploy the website. So, yeah, you will see this live also in the website. So
But I think you could also, I think you should be able to run it without the Quarto plugin.
Now the Quattro install went fast, but installing all the Julia packages.
Ah, yeah, that's taking some time.
The first
Okay, so you're still at on the first slide. That takes.
Just a lot of Julia.
Yes. Yeah, that takes some time because it needs to install all the. Yes, I just realized we should have done that. We should have done a short install all the stuff before the coffee break, but now it's too late. Anyhow, yeah, so now we have this, okay, we can have multiple inputs, we can have multiple outputs. You can also apply functions on moving windows. So say we want to say averaging kernel on all our data. So we can say we can here define a mean filter. So we have an x out, x in. This basically the function is written in a way that it always expects a 3x3 window. So and that's why we say, okay, if the one in the middle is 0, is missing, then the result will be missing, and otherwise it's just the mean of all the non-missing values in my 3x3 window. And now if we want to, so first I wanted to plot this. So this is the input results, the input, which is basically the result of the computation we did before. So this is the mean over time. And now because this image is not blurry enough, we make it more blurry. So currently we have to basically define it by hand, which is a bit annoying. So we're currently in the process of redefining the interface so that you could say, okay, it's a 3x3 window on all of your inputs. So here we currently, so I hope that we will have better interface for this in the future, but currently we have to, okay, we take the dimension of our input cube in latitude and in longitude. DLAT is not defined yet, okay. And so DLAT is the dimension in latitude, so it has a name, it has certain values, so it's sampled, it's of type float 64, whatever, and it's on a range from minus 88.75 to 88.75. And now we unfortunately also need to define this moving intervals. This is basically doing this moving window in coordinate space, but we'll find a way to be able to define it in index space, because yeah, currently it's easier to do it like you could basically say, okay, I want 10 degrees every 5 degrees, and then you could have also overlapping intervals. But for this moving window operation, it's a bit of a hassle to define this. But here basically we say, okay, we take the center of our window is all the latitude values. The width is always 3 times the step size of our latitude dimension. It has as many steps as you have latitudes, and the step size is the same step size as the dimension. And we define the same for longitude, and now we do this windows function, which basically makes a bit clunky named windowed array view. So basically it has as dimensions, it has this longitude, latitude, the same time as the input, the same variables as the input, because we didn't do anything to the time and the variable. But then if we now do what is a bad example? If we now take any thing here, this is a view of 3 by 3 into the input array. So here we defined the input array, and so here we see, okay, this now knows, okay, I need the values, I need the 3 by 3 matrix in this of the input data. And now that we have this mean windows, we can apply our mean filter, which we defined, so which is the function that we defined earlier, on these inputs, on these views of, so the view is just, okay, give me the data that is laying on these 3 by 3. And if we apply this, and then immediately plot it, you want to add something? Please go ahead.
Yeah, I just want to point out that can you go back, show here in the REPL, go up.
Wait. Okay. You want to first that? What? Where?
No.
Scrolling.
Scroll. Yeah, scroll.
Where?
And then go in the main window there.
This one?
Yeah, that. So you can always see like here loaded in memory, right? So, but that happens if you're explicit about it, or if it fits into memory. If it doesn't, then it will say loaded lazily. And yes?
I think that one is lying to you.
This one is lying to me?
Yes.
Why?
because I think the windowed view should not be loaded.
Yeah, that's the point that I was going to.
Okay, go ahead.
So, now what I wanted to say is that yes, when you apply even the xmap function, I mean the last step that Felix did, by default it would be a lazy operation. So if your data set is like really big, again terabytes of data, you will need to do another function like compute to SAR, and then it will do the computation, and then it will save all the outputs into a SAR file. That's the thing that I wanted to add.
Yes. So as you, yeah, we can show that in the, I think, mean. That is, so here this mean TS. I mean, for these data sizes, it doesn't matter much. But as you saw that, for example, here our input cube is a cube of 1.6 gigabyte of data. That is not that big, but it's living somewhere in Germany at the moment. So would be annoying to download it for. So, and basically, this is the stuff that I show here is fast because I only show you one variable. So I only show you a 40th of the data that is actually, could be available. And yes, as Lazo said, you always have this loaded lazily here. And then this mean TS is a result of this xmap function, which is also loaded lazily. So, and then it's computed, as Lazo said, either if you say compute to ZAR, or there's a read cube data function, which basically loads the data that loads all the data that backs up your YAX array into memory. Or if you plot it, it will compute the stuff that you need for the plot. Because yeah, if you plot it, I expect that you want to see something. So, and now as we see, we went from, we applied this mean filter on an already very blurry image to get a even more blurry image. Yay. Yeah, so that's how you could define this on moving windows. And yeah, I think that this moving window operation is a bit strange, but you can basically tweak these steps and these keywords to make it into more to fit what you want to do. Then you can also, so we can also define new output dimensions, which you basically haven't seen before, because so far the outputs that we had were either complete reductions or just taking the same dimension you already had in your input. What we're doing here is like we take a time series of GPP, and we want to decompose it in parts. So we want to have the anomalies, and we want to have one smooth value. Okay. Yeah. So this is one GPP time series from 2000 till 2019, and now we want to, so I specified that I want this time and I want it to have only 1 point. And now I can, yeah, as I said in this, now I can apply this signal decomposition.decompose, which basically takes any time series and, or actually any vector, and gives you back 2 vectors, which are, one is the smoothed version and one is the anomalies. And so I hope this is going to, yeah. And now here, this is again kind of an example of multiple dispatch, because here this GPP is this subset of our data that we loaded with YAX array. So this is a YAX array, as I think I can show. Like I didn't load it yet, but it's similar to this. Why is it not working? Is it? You sure? Good. So here we say, okay, we have the gross primary productivity, we have a certain time span, we have a longitude, we have a latitude. This is also a good, I think, while we are waiting, I can also talk a bit about the indexing in dimensional data. So there's basically two ways you can index into this array. You can either use normal indexing with integers. So you can just say, give me element 1, 1, 1, 1. Or you can use these keywords, like you can use the names of your axis, and then you can also use, so you can say, okay, I want a time axis, and then you can also say, so here we say, okay, I want all the times that are between the beginning of 2001, so date of 2001 is actually is the 1st of January of 2001, until the 31st of December in 2018. And then you also have a few keywords that you can use as selectors for indexing in coordinate space in dimensional data, which are, I think the most important ones are at, near, and where. We saw the where earlier, where we said, okay, give me everything that contains temp in our categorical names of our variables. Here I say, I don't know the position of my point exactly, or I don't know the grid that is exactly at this point, so I just want to know, I want the data at this point, but I don't, just give me the nearest grid location to that point. So this is what near is. If you would use at here, okay, something broke, but I will look into this. So if you would use at here, this would most likely fail because it says, sorry, but there's no good position here. So it's a bit safer to use near, but then it could happen that your point is outside of your area or outside of your raster, and then it would still give you the nearest point, which would be the edge. So that's a bit the trade-off you can have there. So it's just, and yeah, I think, and then you can, with near, you can also, with near or with at, you can also define the approximates. So with at, you can say, how approximate do you want to be? Because it's floating points, and floating points are a bit weird, so you don't always, being at the same exact floating point position is hard, but then you can say, okay, how much can you approximate it? And now I am confused. No, okay, yeah, there is still a bug, which is that I can't, for some reason, apply this on a single dimension. Good. Just take it for the whole thing then. That won't work. No, that is not working. Yeah. No, I'm confused. Yeah. What? That works, but that doesn't. As I said, rough edges sometimes. Are there any questions to the indexing or the stuff I showed before? It's not supposed to run like this. Oh. Do you still think this is a... Wait. I can go to the next, yeah. So what I wanted to show, I could... Maybe I should just show it here. So the
10 minutes.
What?
You only have 10 minutes now.
Why?
No? Schedule is at
12:30, no?
okay.
Okay, yeah, but anyway. Yeah, what I wanted to show is like this decompose gives you a, like it converts your one time series data into two time series data of one is the anomalies, one is the smoothed things, and now we want to do this also on the, so basically we want to apply this on all of our spatial positions and not only on a single one. So here we again define an inner function which says, okay, again, if anything is none, then just get out missing, otherwise decompose it, and then, okay, here we say everything on the first position is the smooth data, everything on the second one is the anomaly data. And then we can again use this X-map on a, so here we just say, okay, we want to have a subset of the data. What? I'm confused. And then we want to decompose it. And here in the output, I basically define, okay, I want the same time axis because I take a time axis, but I get also return a time axis. But then I also define a new dimension, which has a scale, the name scale, and which has two entries, seasonality and anomalies. And why is this not running? I don't know. And now we see here, okay, we now have a time axis, a scale axis, and the two longitude, latitude axes, which are basically the same. And as I said, sometimes your analysis might not be available in Julia, so you can use use Python call or rcall to call your Python functions or R functions. So here we just use SciPy for some Gaussian filter as an example, but you can use this Python core package. You can use conda pkg, which is like to install any Python packages that can then be used in Julia. So that is fast because I already did that before, but otherwise it would take another half an hour or so. And now here we say, okay, we have this scipy nd image, is this imported scipy.nd image from Python. And now you can call a function from Python, apply it on our inputs with certain arguments, and then save this output into a data cube. And now we can apply this on our data using the xmap function again. So if you just use, and you can do the same with R. And yes, as Lazaro said, I'm not going to run this, but basically to show you the idea, as Lazaro said, this is developed for large-scale data and larger analysis, so you can basically run it on whatever hardware you have. So you can use this distributed, which is the standard library for distributed computing in Julia, or you can use it on multiple threads, or you can use it on cluster managers like Slurm. So there's also packages like Slurm Cluster Manager where you can say add procs, and then it just adds all the available machinery that you have when you're in a S-batch, so that you can just run your Julia from an S-batch to just use all the processing power you have. And basically and then Yaxrace and XMap will use all the available cores and memory you have under the hood with only a bit of things you have to change to your analysis. So first you have to, this is just defining, okay, how many processes. So we add 4 processes here. And now we have this add everywhere, which basically runs code on every worker that is available. And then you have to load your package or activate the environment you want to use. You have to load the packages that you want to use, and then you can do any xmap functions, and it will use the processing power that you have underneath, so that you don't really have to change your analysis code. You only have to add a bit of boilerplate to it to make it run on the available processing. Are there any questions? Is there things I should add? Yes. Wait, it's off. I think here, yes.
So, there are documentation for this. Is it working? Yes. Documentation for these packages we have seen here.
Yes, in principle there is, but if
I mean, for example, if I type question mark and the function which has been used there, would it?
why? No, I didn't push it. I wrote a bit of doc strings yesterday, which is on the other branch, but I mean it's relatively new. I would be very happy to write documentation with any one of you, because sometimes it's hard to, as a core developer, hard to document stuff because you're like, I'm just using this and this and this and this, and then like, what are you doing? So I think, yeah.
But still, we show the documentation.
But that is, I mean, yeah, XMAP is not yet fully documented, but I will definitely work on that this week. So also doing the code sprint. But other than that, there's also a main documentation at Yaxaways. So normally the documentation is always if you go on the GitHub page and then you can go to the stable docs and then you have a main but why is this not sorted? I'm confused. Yeah, and then there's some documentation on how to use it. Yeah, but always happy to write more docs. Yes?
How do I create my own documentation of my Julia code in the code file?
So the question was how to write your own documentation?
Yeah, is there a common standard if I create my own functions and I want to document them?
So if you want to document, so there's if you want to write your own function, so what did we do? We had this mean filter, right? And now we could have, where was it? Somewhere it was, I don't know. We have this, right? And then you do, so in, wait. I'm confused. So, like, there's this 3 quotation marks gives a multi-line string in Julia. So now you can do so the decompose the input x. Now you can just basically write a doc string x in and write the decomposition into x out. So basically the Julia REPL will use every string that comes before your function definition or your struct definition as a doc string to that function. So if we do this, now, that was a bad idea. Yeah, and now you see there's a doc string on that, right? Yes?
And how would you write code that is to be run in a production environment that you, for example, would want from a shell or a command line? I repeat my question. How would you write Julia code to be used in a production environment? Not in a notebook, but run in a processing system.
Script. So you can run. I mean, basically, you can, if you would. So depends a bit on. I mean, if your production environment still has Julia on it, you can run Julia my script.jl, and then this will run whatever is in your script.
I'm interested in the Julia way of writing what we know in Python as argument parser.
Yeah. Okay. Yes, there's that is also available.
In that example that you put,
Which example?
the one before.
Argparse, right? So there's this. There's the Argparse package. Wait. let me quickly search for the example for this, because I think the easiest would be to do this RQAD4.
Instruction code, I usually do what he was showing at the beginning, like Julia, name of the script, .gl, and then the input arguments. Like I usually do at least like, I don't know, first argument is index, second argument is, I don't know, categorical variable, third argument is something else. And then within the script, I parse those values as a new variable.
Yeah, but you can also, there's a, so it will either get the list of everything after the script, just as a list, and then you can use that. Or if you would want to be a bit more fancy and a bit more helpful to your colleagues that might want to use your script as well, you can do something like this. So you have this argparse package where you can basically define an argument passes, and I think the way you're looking, it looks like I should increase the size. Can you read it? Yeah, and here you can basically define, okay, minus threshold, and then you can have a help function, you can or a help script that is then shown with my script, Julia myscript.jl minus help, and then you can use define default values. You can define the type of your thing so that it would already convert your command line arguments into certain types. And yeah, so you with this argparse you can just write this, and then and then you can use this then from a command line. I think I can also show you this quickly, maybe if I find it. Yeah, what? Oh, yeah. Yeah, okay. No, I don't know where this is currently. But
Such an example into your reverse code?
the argparse?
Yeah.
Mm-hmm.
A small snippet like
Yes. I can at least write the argparse package so that you know the package name. And then there's a argparse. Yeah. Then there's documentation on that. Yeah. Okay, any more questions?
Final comments.
Otherwise, I will show.
Yeah,
Go on.
continue.
No, please.
Could you just maybe sum up again how I can expect this workflow to be different from a XRA-based workflow with Dask, for instance, in terms of runtime or memory use or conveniency?
Do you want to answer?
How to put it? First, I mean, I don't have so much of experience with Dask of Xarray in combination, but a colleague of us has been done some benchmarks, like what you can do with Dask and Xarray, and what you can do with XMAP. And so far, the gain that he has shown is twice. So instead of taking 2 minutes to do a global run, with X-ray and dusk, and for XMAP is 1 minute. So
Another thing that I would say is, yeah, and one thing is that so this XMAP is an interface to this function called, or this package called disk_engine, which is basically I would say the Dask equivalent for what we're using. And I think the main difference is that Dask is constructing this huge compute graph to then do the computation, and sometimes, at least that's what I heard, is that it fails because your compute graph, if your data is large enough, if your chunking is bad enough, you won't be able to run certain operations because your compute graph won't fit into memory. And disk_engine takes a bit different approach and also tries to optimize the chunking structure. So you don't necessarily have to use the chunking that is on disk. I mean, it tries to optimize for data access and also data writing, but it won't fail on larger data. So it will might be a bit slower because it's larger, but it's not just going to crash because your data is too large. And also there's an example that I could show a bit. I mean, I'm not going to run because the data is set up on our cluster, but basically our colleague had this example of actual analysis that we did where we wouldn't know how to do this in Python using X-array Dask. So the use case is we have this error 5 data. We have precipitation data in error 5, and error 5 is a bit strange in how to save it. So they save it for every position they save it an accumulated daily precipitation sum for every day in UC T. So for every day, so basically it's not the local time, but it's the global time. It's all the same. And now we wanted to have we wanted to have daily. We wanted to reduce this to hourly precipitation in local time zone, because we want to we want to compare it to local precipitation measurements. And so this is the script is also in the repository, but basically here, wait, let me increase the size a bit. Yeah, here we load the packages, then we load the data. So here we have a time zone file, which is basically on the same grid as our input data, but basically this gives an offset of your time to UCT. And then you have this error 5 land hourly precipitation data that is on 0.1 degree and from 1990 to 2023. And so you open this as a multi-file data set, and then here we just shift the latitude because we shift the longitude because it's not from 0 to 360 but from -80 to +180, and so I'm not, unfortunately I can't run this because it's in the cluster, but as I said, like the time your time axis looks a bit like this. Right? Because this is daily daily accumulated precipitation. And now you want to say, okay, I don't want to have this. I want to have this accumulated because I want to have it in a different time zone. And where am I here? And so we define this daily diff vector of, okay, if it's so I want to have still the accumulated sum but for the actual local time. So this daily diff is, okay, if it's a 24-hour, then it's just 0. We take the value, otherwise we take the diff between this value and the hour before, because this is the actual precipitation during this hour. And now we want to apply this on every time zone, or on the time zone. So we say, okay, if the time zone offset is too large or too low, then we discard this because we won't have a time zone offset of 20 hours. And then we say, okay, our interest is also the time axis we're actually looking at, so which is the actual time of the local day is the middle of, like I showed a bit later, but here basically we say, okay, we go from the January 1st of 1990 till end of December 2023 by a day, but we take always a 3-day window. So we have these overlapping intervals, and now you can say, and now here in the inner function, we say basically the 25 to 48 is like, this is the middle day of your 3-day window, and now you shift this by your time zone. So you go either 2 hours ahead or 2 hours before, and by that you get the actual time, and then you can lazily, and then you basically make this daily diff vector of, okay, we just make the local diffs, and then you sum the current day to go from this to this time interval. And yeah, that's what we could do with this XMAP and moving intervals, that at least we didn't find a way, we wouldn't know how to do it in XOA. So yeah, and then of course this takes some time because this is, I think, a multi-terabyte data set, but it just runs somewhere on the cluster and then it's done whenever it's done. Any more questions? Yes.
Runtime. So is there maybe a prediction on the runtime an operation would need, given maybe the past operations and some experience on the complexity of algorithms, on the amount of data?
So not in the beginning. So I won't have that. So, but you would, if you would run it if you would run in distributed or threaded, and it would take some time. I mean, these were fast enough that but normally you get a progress bar with an approximated runtime. So normally you would it would say, okay, it basically what it does is like it takes the first, so it takes the work in batches, right? And then it did the first one and knows, okay, it took half a minute for this, and I have 20 more to go, so I will take this times 20. And then it will update itself, the longer it runs. And sometimes of course, there's jumps because it's like what's slowing down because there was some missing values in the beginning, so it didn't work. It didn't do any work in the beginning. It's like oh, it's actually a bit slower. Or sometimes what also happens with Julia a lot is like the first iteration takes a bit more time because you have the compilation, and then it will get suddenly a bit faster because the first estimate was off. But yeah, we have that for larger things, I'd say. What? No. Why is pure no? New not defined. Oh, because I'm stupid. Okay. Yeah, and then I wanted to show another thing. Or if we have the time and there's no questions, I could quickly show pyramid scheme and what we're doing there. So pyramid scheme is a package that also builds on Disco Engine and the underlying work to work with pyramids or so-called overviews in currently in geotiffs or also ZAR data. So the idea is that if you have a very large data set, you won't be able to fit, you most likely won't be able to fit it into your memory, and definitely not going to fit it on your screen. So if we, for example, we have this, we have P, so here we just load the packages, and then this is all, yeah, this is, I'll explain in a minute why we need that. So here we just have pyramid scheme and dimensional data again. So, and then you can just load the data set as a pyramid. So this is a 100 meter above ground biomass data set, which is like quite large. So it's 400,000 by 160,000 pixels. So you won't be able to fit this on your screen. Maybe that, no. But then this data, because I prepared that, comes with overviews. So you have 11 levels of overviews from 400,000 to 198 pixels. And so if we now do this, we have to wait again, I guess. But so here we say so. The fun of compilation, yes, but it's just the first time. So now we have above ground biomass for the year 2020, and yeah, it looks okay. And then you want to go here, you can zoom in, and this will. So basically, what it does is it always loads the data that is only needed for your area of interest. Cool. We had that for 30 years. But now we can also do computations on that. So here I do this broadcasted operation. I have the same, maybe I should do it on the other way around, but anyway. So we have the same data on the same grid for 2017. So we can say, okay, what was the change in above ground biomass from 2017 to 2020? Now if we do we can plot this. Wait, let me fix the color bar a bit. So this is the difference, and I should have done it the other way around, because now red is, I think, increase in biomass and green is decrease, which is a very good choosing of colors, but anyway. And you see, it's a bit slower because it now needs to load 2 data sets. But it's still roughly interactive. And yeah, and then that works, but now we also want to do a base map. So
yeah, that would take even longer. Oh, okay.
So we want to put OpenStreetMap underneath our data so that we actually know where we are. And that is still the green of forest information in OpenStreetMap. But now we can plot a new pyramid on top of that, which is lazily reprojected on the fly to WebMercator. So the initial data is in lat long, which is now reprojected to WebMercator to be able to plot it on OpenStreetMap. Which is now slow because it loads both the data and OpenStreetMap on this internet connection, but yeah.
Okay, I think
Yeah.
that was good.
That was it, and I think for now, so we're open for questions and we'll be around. And as I said, please open issues if you use it and find anything that is confusing or not working as you expected, and we're happy to help. And yeah, and if you want to help write documentation, please come to me and we write it together.
Yeah, I just wanted to say thank you for joining us, and I hope you got something. So, yeah, thanks again for being here. That's it.
Thank you. Yes, you still have questions. There's still questions, so.
Yeah, there's still I
wanted
just to close the session.
So
it's
very specific, I guess.
Yes.
So while trying to run this, I run into trouble with like 8 packages or something. And so what's your approach in these cases?
That's a good
I tried with resolve, I tried with precompile, it seems
can you go up? What's the initial error?
let me see.
It might be that, or can you just do it okay, yes. Precompile is a good first approximate, and then, actually I can, let me first get rid of the microphone. Ooh, funny.